We are going to enter into a zoo, but this time you won't see lots of animals. This time it's the cosmic zoo. There are many things which are in the universe. And Swarnim Shirke, who is a research scholar at IUCAA, he is going to take us on this tour of this cosmic zoo. Hello. Yeah. Okay.
So, hello everyone. Good morning. Welcome to IUCAA, and happy National Science Day to all of you. My name is Swarnim. I'm a research scholar here at IUCAA, working on particular objects called as neutron stars. Now, some of you might know what neutron stars are, but if you are like me, the way I was, or like most of the people, don't know what these stars exactly are. And this is common. This is true for many of the things out there in cosmos. So I was told to ask. I was asked to give a talk on something that would excite everyone. But I thought I'd also cover something where you learn something as well as get excited. So that's why I'm talking about the cosmic zoo. So we know about normal zoo. We go there and we see animals. We basically go and see which are the animals out there. So if you just say what are the animals, cats and dogs, that's not it, right? We have some huge animals like elephants, some smaller ones. So similarly, out there in cosmos, if I ask people what is there up in the sky, people will say stars and planets, but that's not it. And if you go to any research institute or any science institute and ask people what they're working on, they'll give you some terminology which you haven't come across and which usually is not stars and planets. So there are a lot of objects out there which scientists or researchers study. So from zoo, I will take you to the universe, introduce you to the universe, and take you to the cosmic zoo and introduce you to various objects in the universe. So this is up to your interest. I would suggest if you have a notebook or a phone or anything, I won't be showing much. I'll just be flashing some terms. You just note them down if you are interested, because this will give you the entire dictionary of what is all astronomy research about. So I'll tell you about each object. Also, you can go back and if you just Google it up later on, like each of these terms, you would know more than most of the 12th standard or even graduate students know about astronomy. So you will have your own dictionary, and even if you go to any website like IUCAA or you talk to scientists, or if you go out today and see the posters, you will come across these same terms. And these are not just stars and planets, these are the terms, these are the things that astronomers actually study about and do science with. So let's get into it. So I'll start with this picture. We have time. This is the picture of the universe, and on vertical scale, I'm showing the size of the universe. So that is how big the universe is. And this is where the universe started. And with time, you see the size has been increasing. And this is today. It is increasing at an accelerated rate. So here we can see it has been almost 14 billion years that this universe has existed. So, and when astronomers see in the sky, we look in the past. So we can see at different epochs of the history of the universe. So if we talk about just today, what is there out today? So we get this pie chart. So first question we ask is what is there out there? What is the universe made of? We get this pie chart, and turns out, so basically this study of the history of the universe as well as what is it made of, it comes under the umbrella called as cosmology. So this is like the first term. If anyone is noting down, you can just look it up later on. I'm basically explaining it. This is what scientists also work on. So what is the history of the universe and what is it made up of? So if you look at this pie chart, so this entire universe, this entire volume, the biggest component is that of something called as dark energy. So this is a weird kind of energy that is spread throughout the universe, like a fluid. We know some of its properties, but we don't know what it is. That's why dark energy. It has sort of like this negative pressure, which is, and this is the component that is responsible for the expansion, this accelerated expansion of the universe, and it is spread throughout the universe. So this is, you see almost 70% of it, of the energy, like this content of this universe is in dark energy. Next, we come to dark matter, which is around 25%. So this is just matter, it's just that we don't see it. We can feel, as matter interacts via gravity, we can feel its effect on other material things. And we have studied its effect, but it is still, we cannot see it, so it's still dark matter. That's 25% of the universe. And what is left? This 5%, so is all that we see out there up in the sky. So when you look up in the sky or with your telescope, all that you see is this 5%. So coming just more about dark matter. So if we, this is a simulation. If you want to know how this dark matter is spread out through the universe, so this simulation was carried out, and this is how our universe looks like. So there are these gaps, voids, there is this filament, there is these clumps. This is all how this dark matter is distributed. Just like you can distribute gas in this room, this dark matter is distributed throughout the universe, something like this. And the 5% that I talked about, the rest of the things that we see, follows a similar distribution. It follows how the dark matter is there. Wherever dark matter is, we see this visible matter also. But this is all just 5% of the universe, and how this all matter gets structured up in the universe, how is it distributed all across the universe? The universe is not uniform. So all of this comes under the term called the large scale structure. This is where people study the distribution of matter and energy on the largest scale in the entire universe. So now what are these exactly? This is the distribution of matter, okay, but what are these exactly? If you want to know what is it, if you are looking up in the sky, so what are these clumps that we see? So these are actually, when we put our telescopes, we see something like these. So these are clusters of galaxies. So all this universe, these clumps are basically clusters of galaxies. These galaxies is what makes our entire universe. So this is our visible universe, the 5%. So cluster is like a lot of, like hundreds and thousands of galaxies which are very nearby to each other. They have clumped up, so each individual of them is a galaxy. These are called as galaxy clusters. And some of these galaxies are also formed with tiny clusters. So here we have hundreds and thousands. So, but if we have only few galaxies, few tens of galaxies which are nearby, we term them as galaxy groups. So these are also two terminologies. If you'll find even people at IUCAA work on this. So when we are talking about clusters and groups, we also study about how these galaxies are interacting with each other and affecting each other's evolution or growth, and affecting each other, impacting each other in general. So these are two things: galaxy clusters, galaxy groups. These make our large scale structure. Okay. So what about the space in between? So we have, each of these is a galaxy. This is a galaxy. So the space in between, or the voids that we are talking here, it's not completely empty. It's not vacuum. It's not nothingness in there. So there is also gas. Sorry. There's also a lot of gas in between these galaxies in the empty space, which is not directly visible since it's more spread out. And that is also has a name. It is called the intergalactic medium. So we have galaxies, and the space between these galaxies is filled with intergalactic medium. It's also a gas, and this is also an active area of research. So people just study this. There are groups all over the world who just study this particular medium. So as I told, these are individual galaxies, but around these galaxies, so we have intergalactic medium. But just if you take isolated galaxy, it's not visible directly through our images, but this galaxy is surrounded by a lot of diffuse gas just around it. So it is not part of the intergalactic medium that is between two galaxies, and it is basically a part of this galaxy, but like around the galaxy. So you see, if this is galaxy, our small galaxy. This is the scale of the gas that is part of the galaxy. So it heavily affects the evolution of this galaxy also. And this gas around it is termed as the circumgalactic medium. So this is also, it has become a very active research area for astronomers. People are becoming more and more interested in studying the circumgalactic medium and how it affects the galaxies. Yeah, coming back to what I have been talking about, obviously all these individual building blocks of the universe that I have been talking about are galaxies. So there are scientists or like researchers who just study on the galaxies. They're not talking about intergalactic, they're not talking about cosmology. They just want to study how this galaxies or like the dynamics of it, how it evolves. So this is, I think most people or many people might know this term already, just like stars, planets. There are also galaxies. There are a lot of about 100 billion galaxies out there in the universe. So the large scale structure that I showed, so that is the entire observable universe. So we have about 100 billions of these. So this is our building block. Now some of these galaxies, if you go ahead, some of these galaxies have very bright core. Not all, but some of these have a very bright core. And these regions are very active. Sometimes it is so bright that it outshines the entire galaxy. So galaxy is something we see as a point or like a fuzzy thing up in the sky. But sometimes this core, just the central part of it, is so bright that it is brighter than or like comparable to the entire galaxy itself. So these at the center, if we have this activity, heavy activity, that is, it's the nucleus of the galaxy. So it is called as the active galactic nuclei. So it is active, it is part of the galaxy, and it's at the nucleus of the galaxy. Usually, so we get the radiation, like this activity from this disk part and the jet part of it, and there's a black hole, like a supermassive black hole at the center of these galaxies. So this is active galactic nuclei. These are all the terms that you will see on if you go to any website of any astronomy like IUCAA, or even the US ones, Harvard, Caltech, you go to astronomy page, you'll find these terms, which people might not be aware. So this is active galactic nuclei. This is also a popular field. So coming back, so that's the nucleus. Now what is this galaxy? What is the other part all about? So galaxy is obviously this, but what is it made up of? So if we zoom in into some different part, that is basically the stars that we talk about. When we look up at the night sky, all the twinkling stars that we see, these are the stars that we are talking about. That is mostly what we see up in the sky with our naked eye. And these are the stars that make up a galaxy. So about 100 billion of such stars that we see in the night sky, this is what make up our galaxy, Milky Way. Similarly, other galaxies, which are also about 100 billion, each of those galaxies are made up of stars like this. So if you sit in another galaxy, you will also see stars like this. Those are also 100 billion of them for each galaxy. So this is star, or the technical term would be stellar physics. So when people just study about these stars, they're doing stellar physics. Now, some stars come again in very tight clusters. So just like galaxies we saw were in galaxy clusters or galaxy groups, so we also have groups of these stars. So we have a lot of stars which are packed very tightly together. Just like, you see, like there are some isolated stars, there are also binary stars, like there are two stars orbiting around each other. And there are some clusters that I've shown here. So the evolution in of a star in star cluster is different from that of an isolated star. So this also makes an active area of research, the star clusters. Okay. So coming back, just like galaxy, it's like we're zooming in. We're going from elephant to some tiny creature. So just like in the case of galaxy, in between two galaxies we had gas, we called it intergalactic medium. In between two stars, or within the galaxy, we have stars, but the rest of it is not completely empty. So we have something called as the interstellar medium. So there is also gas in between these stars, there's also different type of, we also have dust and molecules. So all of this make up something called as the interstellar medium. So there are people who also just focus on, in their research, just focus on the interstellar medium, because all of these, each topic that I'm like listing out here are an area of research itself and are interesting. All of them are very interesting in themselves. And that's the interstellar medium. Here I've shown the Milky Way, the disk of the Milky Way. This is how we see the disk. So we see stars, but when we go at the disk of the Milky Way, our own galaxy, we see these black patches. These are like the dust which is there in our own galaxy. So this is also part of the interstellar medium. So it is blocking all the light that comes from behind it. So it looks like this dust. Okay, so these stars. What are these stars? Individual stars. I think everyone probably knows what are stars. Stars are objects like our own sun. So sun is a star, as you might know. So all of these stars are just objects like sun. They might be different. They can be tinier. They can be much larger. There are like, each of these is a zoo in itself. So each of these topics. So I'm just showing this sun. So all of these stars are basically sun-like objects. They are gas which is producing its own energy at the core. So it's nuclear energy which is burning at the core of these stars, and it is giving out light. So these are the objects, finally, these are the objects which are giving out light in the universe. So all the light that we see up in the sky are eventually, mostly, coming from some of the stars. Even galaxies that we are talking, it is made up of stars. So light is being generated inside these stars. So it's like stellar physics. I'm showing here the sun, and sun, again, it's a very special star because it's close to us, it's ours, it's a part of our solar system, and we can see it very well, and we can study it very well because it's very near us and it's large. Recently we also launched Aditya L1, right? You'll also see out there. So it studies just the sun. So the study of the sun and how it, the different parts of it, different regions of it, and how it affects the earth, this all comes under umbrella called as solar physics. So it's just the study of our own sun. Just I wanted to show an interesting image. So since it is the closest and it is easily observable, we have very good data, and we have seen it in various wavelengths and filters by different telescopes. So this is how the sun looks like in different filters, or like when we are probing different regions of this sun. So this is solar physics. Now, most of the stars, so like just like our own sun, have their own system. So we also have the study of our solar system. Just like in the previous talk, if anyone was there, Jitendra talked about the solar system. So he talked about the sun star and the planets, and there are a lot of things like asteroids. So we get some event comets, Pluto over here. So this makes the study of solar system. I want to mention, so this is our own, but just like we have stellar physics, we study stars outside. Every star would have their own system. So they might have their own planets. So when we do that, so suppose this is some other star and this is some other planets. So there might be planets which are habitable for, or like can sustain human life too out there. So if you are studying their planets, we term that field as exoplanets. If you are studying the planets of some other star, and so there are different techniques, and we have detected quite a few. And if you're studying them, and if you're studying how is the habitability and everything, so this is exoplanets. This is a very interesting field because it is associated with life, whether there is life out there, there is alien civilization, because these are very catchy terms. But scientifically, this is the study of exoplanets. You want to study other planets out there. So coming back, now I've talked about stars. I won't go into the solar system. I'll talk about more interesting objects which are associated with all the stars. So when stars like sun, or even other stars, more massive stars or even less massive stars, they are associated with certain objects. So they're associated with certain things which are associated with their birth as well as death. So when stars end their life, when they end their fuel at the center of or at their core, they undergo a huge explosion. So fuel runs out, the star matter like collapses inside and then rebounds and gives a large explosion, and we call it something called as supernovae. So supernovae is one of the most violent events in the universe. It gives out a lot of energy, and it forms something. So a star collapses and goes into the core, and the outer regions of it are shed out into a huge this nebulae, which will come to this sort of a nebulae. And this event is called as supernovae, which is an interesting event all in itself. So if a massive star explodes like this, we call it supernovae and forms this nebula. If a sun-like star explodes, it also forms a similar kind of structure, but a different one. We call it planetary nebulae. So all these things are called nebulae, nebula, or in plural nebulae. So these are basically clouds, just like we have clouds in the atmosphere. These are clouds of the material that the star was associated with. So also there are other types of nebulae. So if we look in our this Milky Way itself, we find these clumps of gases which is slightly cooler. So it's just gas which is coming together, it has formed molecules, and it is cooling down and it's coming together and it's forming these sort of dusty-like patches. This is where star formation takes place. So if there was no star here, it's just the gas coming in, like the interstellar medium that I talked about. It comes in and becomes dense enough to initiate star formation. So when this matter clumps more and more and more, we'll have stars forming in the regions like this. These are also called as nebulae. These are like some images of how nebulae look like. These will have star formation after in the future. These are all associated with the death of the star. So after the star has died, and this is where stars form. All of these are called nebulae. So as I said, when star explodes, the core remains at the center, and the outer layers are exploded in the outer shells. So even for this, if you go at the center of these supernova or planetary nebulae, we get what are called as compact stars. So compact stars are a class of stars, but it's so different from stars that it's an area of research all in itself. So there are different types of compact stars. So here I'm showing white dwarf. So it's like mass of us, it has something mass, like if when sun, it will run out of fuel, it will form something like this. It has mass of this, that of sun, but it is size of the earth. We know sun is very much larger than earth, but eventually it will form of the size of the earth, and we'll call it as white dwarf. So physics is entirely different in compact stars, and people work on white dwarfs itself. Or if we have slightly massive stars, instead of white dwarfs, at the core of these supernovae, we are left with something called as neutron stars. So these are even more compact. So if we have mass that of a sun and compress that sun in the size of a city like Pune, so it's very, very, very small. It's very compact. That's why it's in compact stars. So we call them as neutron stars. And we observe neutron stars. So these are two terms which you might find in the posters also, or even different websites, or if you look up any astronomy research anywhere. So these are two. So pulsars are neutron stars which we observe. So these are not two different objects as far as we know. So these are neutron stars which we observe as observed through a lighthouse effect. So these neutron stars give out like jets. So when these jet, like a light beam, when it reaches us or like sweeps our earth or passes our line of sight, we get a bump in light. So we observe some pulses coming from these neutron stars. So those are termed as pulsars, but these are the same objects. And even if the star is even more massive and it goes supernova, so we get something even more compact like this, which a lot of people might have already heard. These are called as black holes. So these are one of the compact star that we have. So it's just a black hole. It is so compact that even light cannot escape it. and that's why it gives this black patch where we don't get any light from. This is the light that we get is from the surrounding of it, but we don't get any light coming from the black hole itself. So this is these are black holes. So these are what I wanted to talk about, the compact stars. Also, so these are the objects. So also when these compact stars go, or if we have binary systems, they go about each other. We give out something that Einstein predicted 100 years ago. We get gravitational waves. This is a very recent, it is an old topic, but since we have detected gravitational waves about 10 years ago, since then this field has boomed because now we have finally detected it, and a lot of new projects have also come up, like LIGO India coming up in India also. So there is these gravitational waves which are spread throughout the universe. So it's up to us to detect it, but this is also what universe has. So it's so we have a special kind of detectors. These are not optical, but this is spread throughout the universe, and this makes another field of research. These are gravitational waves. These are waves in the gravitational field that is given out by these compact stars, since compact stars have the strongest gravity. So coming back, just to remind you that all the things that I showed today, I know there was a lot of terms. It's good if you have written it down, you can refresh it later or something. But all the things that I showed today, right from the large scale galaxy clusters to these compact stars, I was just talking about this 5%, just to refresh your memory. So all that we talked about, all these objects, all these beasts are there up in the sky, and these make up 5% of the universe. As we cannot see these other rest of the dark energy and dark matter, they are not directly visible, but we feel their effects. So there's another component, finally, that I would like to talk about. So this makes up 100%, but I have not shown one thing in this pie chart. So there's one more component, but it is so tiny. It's like 1 in 10 raised to 5. So like 0.001% of this entire universe. That makes up the radiation component. So radiation, as we know, we have electromagnetic radiation. Gravitational wave is also a form of radiation. So all this radiation, the lights, or if in scientific terms we term them as photons. So they are spread throughout the universe. So they were there right from the beginning of the universe, and it is still there. So this radiation we have detected, and it is seen to fill up the entire universe. So if we are focusing on this particular radiation component, which is very tiny, but it gives a lot of information, we come to the study of the cosmic microwave background. So microwave, because it's an electromagnetic radiation and its frequency lies in the microwave, like we have microwave ovens at our homes. So similar wavelengths we have. Cosmic, because they are of the cosmic origin, it's there everywhere. Like we catch them in old TV signals when we don't have network. The noise that we see is also part of this cosmic microwave, and background because it's there everywhere. So this is also a term that you will find everywhere in astrophysics research. This is the cosmic microwave background. Similar to microwave, we also have neutrino background. Neutrino are the lightest particles, but since they are light, they are so fast, they act like this relativity, or like radiation, that behave like radiation. But our neutrino detectors are not yet so advanced that we can detect this background. We are just recently made some progress on it, but there's that. So yeah, so this makes up all of these things, the dark energy, dark matter I showed you, from galaxy cluster, large scale structure, galaxy clusters and groups. We come to galaxies, to star clusters and stars, and within we have intergalactic medium, interstellar medium, we have circumgalactic medium. Stars have their own planets, exoplanets. Stars are associated with supernovae and nebulae, where they form and they also die. And supernovae, or like these explosions, are associated with compact stars, like very compact stars, like white dwarfs, pulsars, neutron stars, and black holes. And this background of gravitational wave, neutrinos, and this microwave. This is all what makes our universe and our cosmic zoo that I wanted to introduce you to, all the beasts in the universe. So, yeah, that's it.
Thank you. So, if you have questions, you can raise your hand. Yes?
We have universe, and light has a limit on speed, which we call as speed of light. Nothing travels faster than that. So given that we have had the universe for 14 billion years, there is only up to a certain distance that we can actually see. So light beyond that has not even reached us. So that is our observable universe. And when we say it's growing, so within this observable universe, if we take any, as I showed, the universe is made up of these galaxies. So if we look at these galaxies, it turns out that when we see them in this observable universe, every galaxy is going away from every other galaxy. So it's like a rubber sheet, and if you put 2 points or like multiple points, and if you stretch that sheet, all the points will go away from all the other points. So this stretching or like this growing of the distance is what we call as the expansion of the universe. And this also affects the observable radius, since it is, as it's expanding at accelerated rate, the size of the observable universe goes on reducing. So there are objects which are with distance become so start receding from us so fast that it escapes like the speed of light, so like we can't even reach to them. So that is what we mean by expansion.
Thank you. And
that is why the study of the past or cosmology is also important. So if we know these components, so what is it made up of? How much is dark energy, dark matter? Or if there's one more thing, like the curvature of the universe. If you know all these things, it becomes possible to predict the future if we then apply physics. So for physics, we need to know what is there initially, and then we can evolve. So there are like different possibilities, like you might have heard like big rip, big crunch, or like just this, just ever growing, but we don't know for sure yet.
thank you so much. Okay. Thank you. So thanks all for attending.